be chairing this session for an hour, and Jacek will take the second part of the afternoon. So the first speaker today is Markus Wolff from the University of Tübingen, and he will be talking about evolving surfaces along their inverse space-time mean curvature. Please, Markus.
Thank you very much, and I want to thank the organizers for the opportunity to speak. So today I want to talk about a joint result with Gerhard Huisken from the University of Tübingen about the evolution of surfaces along their inverse space-time mean curvature, which is an adaptation of inverse mean curvature flow in the context of general relativity to initial data sets. Sorry. Here a rough overview over my talk. So I want to start with a brief introduction motivating this adaptation, and then I want to present our main result, which is the existence result of this new flow under consideration. And after a brief sketch of the construction, I also want to talk about some properties of the solution, mainly the development of jump times and the asymptotic behavior. And then I want to give a brief outlook about open questions. So let's start with the introduction of initial data sets. So we consider an asymptotically flat Lorentzian manifold governed by Einstein's equation with stress energy tensor T. And here asymptotically flat means that outside of a spatially compact set, we consider our Lorentzian manifold to look roughly like Minkowski space. And inside such a Lorentzian manifold, we consider a space like hypersurface Mg with second fundamental form K. And then we call such a triple MGK an initial data set. And through the Gaussian-Kodazzi equations, MGK satisfies the following constraint equations, where we note mu as the energy density and J as the momentum density. And we say such an initial data set satisfies the dominant energy condition if mu is greater or equal than mod J. And lastly, we say our initial data set is time-symmetric if K vanishes identically as a tensor, and maximal if the trace of K identically vanishes across the manifold. And in this context, Huisken and Ilmanen used the weak notion of inverse mean curvature flow to prove the Penrose conjecture in the time-symmetric case. And here, this weak notion of inverse mean curvature flow perfectly fits the notion of an apparent horizon in time symmetry, namely that it will be given as a minimal surface. But this is in generally not true. Such an apparent horizon will, for example, arise as the intersection between this initial data set in the Lorentzian manifold and the boundary of the trapped region. And if the initial data set is extrinsically curved there, then such an apparent horizon will no longer be a minimal surface. So the idea is now to adapt inverse mean curvature flow to initial data sets by better fitting it to the horizon geometry. And since I've mentioned this Penrose inequality, I also want to make clear that at this point, for this adaptation, we're not talking about any monotonicity of like a quantity like a Hawking energy. So rather, let's talk briefly about apparent horizons. So we start with a hypersurface sigma in our initial data set, and we denote its mean curvature by H, and the trace of K along the surface is P. We then define the future and past expansion of such a surface, theta plus, theta minus, as H plus minus P, and its space-time mean curvature as the square root of H squared minus P squared, which is equivalently the square root of theta plus times theta minus. And then we say such a surface is a marginally outer or inner trapped surface if it's theta plus or theta minus vanish identically on the surface, and we call sigma a generalized apparent horizon if curly H is equal to 0 everywhere. And also following observation, of course, a marginally outer or inner trapped surface is always a generalized apparent horizon, but the converse is not true. And there's an explicit counterexample by Carrasco and Mars. Now, having this notion of apparent horizon, we go back to classical inverse mean curvature flow, which is just a smooth parabolic flow where the speed in the normal direction is proportional to 1 over the mean curvature. But we can also equivalently describe this parabolic problem as a weakly elliptic partial differential equation for the time of arrival function u. And here, such a time of arrival function u, we understand as a function that on the initial surface is 0 and acquires the value t at a point y exactly when y is on the surface sigma t. But both of these notions of inverse mean curvature flow require strictly positive mean curvature or the notion of a unit normal as the gradient of u. So in particularly, we cannot encompass jump times in this notion of solution. where we would assume that our time of arrival function can be constant on a whole open neighborhood of our manifold. And to do this, we use this weakly elliptic PDE as the Euler-Lagrange equation and determine the variational principle lying behind this Euler-Lagrange equation. And it turns out we achieve this by freezing this mod gradient U term into a comparison principle and prescribe. And so for every prescribed function, which is locally Lipschitz U, we say this is a weak solution to inverse mean curvature flow if U minimizes its own comparison principle with respect to any competitor V that differs from U on a compactly contained set. And now modifying this with the notion of apparent horizon, first let me talk about a generalization which was first considered by Kristen Moore in 2014, which she called inverse null mean curvature flow, where instead to flowing in normal direction with respect to 1 over the mean curvature, we now flow with respect to 1 over the past or future expansion respectively. And this adds this additional P term into the weakly elliptic PDE, where here we still have this notion of gradient U divided by mod gradient U as the unit normal. But of course, as we want to get rid of this in the jump region, this now gives rise to this additional term here in the bulk term, which requires a notion of unit normal, even across jump time, so where our function is constant on a whole region. So instead of just saying our solution is the function, we now require a pair of a function and the unit normal as a weak solution, and prescribing it to this comparison principle, we then say U minimizes this comparison principle with all competitors. And now we consider this new flow under consideration by us. We call inverse spacetime mean curvature, which the flow speed is proportional to 1 over the spacetime mean curvature. And this is in particularly motivated by the recent work of Zederbaum and Sakovic, where they defined a notion of center of mass with respect to constant spacetime mean curvature surfaces.
May I ask a question?
Yeah, of course.
Because in the last line you still have gradient U square. Oh, that's a derivative. So that's so one gradient stays and one is replaced by new. What's the?
Yes, exactly. Because if you now this variation allows for a gradient U to be 0 everywhere. So that's why this problem is not there in inverse mean curvature flow. But now across jump times we still need this unit normal. So we need to find a particularly replacement for this in jump regions.
And how do you enforce at the end that nu is the gradient? That's part of the game at the end or something like that?
So that's exactly, nu is no longer the gradient across jump regions. That will be one of the key features of the construction.
But it should be in the smooth region, right? So
yes, for smooth solution will be the case. Like maybe wait one more slide and I'll elaborate on that a little bit further. Sorry. So just as this question suggested, we now need to deal with this anisotropy where we have this new normal. And it turns out instead of just formulating these weak solutions on the initial data set, we rather go to the cylinder over the initial data set. So to be a little bit more precise, what we now regard as a solution to initial data E0, we no longer just define it only on the initial data set, but rather we go to the cylinder M without E0 cross R, and there we require a pair of translation invariant function U and unit vector field nu, where nu is translation invariant, but not necessarily tangent to the original initial data set. And then we require U to minimize this variational principle on the cylinder. And outside of jump regions, nu actually will agree with this intuitive notion of unit normal. But inside of jump region, we now see that they are in fact in the cylinder foliated by generalized apparent horizons. And therefore we can define nu there as the normal to this foliation. So does this deal with your question?
Yes, thank you very much. Yes.
Okay, great. And lastly, since we still think of U as the time of arrival function, we require it to be non-negative and to approach infinity as we move to spatial infinity. And the main result is now that on asymptotically flat, initial data sets where we have a restriction on the dimension because of regularity theory, we actually require, we get a solution for any such initial data. And also we need this maximal condition. So for now, we assume that the trace of the second fundamental form K vanishes everywhere on M. And I'll elaborate why we need this in the construction. So now how do we prove this? So this strategy is similar to the original strategy by inverse mean curvature flow. So we construct explicit candidates, and we start by constructing a candidate for the solution, for the function. And the idea is very similar to inverse mean curvature flow. So we start with this weakly elliptic problem for our time of arrival function, and we transform it into a strictly elliptic problem via elliptic regularization. And then we establish for each epsilon small enough the existence of these solutions, and we see that by a locally uniform C1 estimate, we can actually extract a sublimit U, which is locally Lipschitz everywhere on the manifold without the initial data, which approaches infinity as we move to spatial infinity. And by a barrier function constructed for this elliptic regularization, which explicitly uses this maximality condition, we actually can push our sublimit to be non-negative. And that's why exactly where, for now, this maximality condition comes into place. And now we have found this candidate U, still only on the original manifold, but we still have this issue that we now need to construct a unit normal. And here we start exploiting this additional direction. So we add this another dimension by going to the cylinder M cross R, and we extend the metric and the second fundamental form K in a trivial way. And then the key observation is that we have this function of the solution of the elliptic regularization. Then this function big U of epsilon, which are U epsilon minus epsilon times Z, is in fact a smooth solution of our original problem. And the level sets are given by these translating graphs. And then the idea is that also on that we have this locally uniform convergence to our candidate U, even on the cylinder. And moreover, we have this translating graphs that in some sense foliate our cylinder. And then we can just study the limiting behavior of this translating graphs to define our notion of unit normal. And we do this in the following way. We observe that the sub-level sets, in fact, satisfy a variational principle. And this variational principle now allows us to use a regularity theorem from geometric measure theory. And this is where our dimension restriction comes in to get locally uniformly C1 alpha estimates for our limiting, for our translating graphs. And now using Arcela-Ascoli, we can actually extract limiting surfaces, sigma h, which are still in C1 beta. And now we can actually use these limiting surfaces to find our unit normal. And then employing a compactness theorem, we have constructed this weak solution. And to further elaborate on this definition mu of these limiting surfaces, we can distinguish between two cases. If, for example, t is not a jump time, then we can actually show that this limiting surface is just the level set of our candidate U. And therefore, this notion of mu as gradient U divided by a mod gradient U is satisfied. And in jump regions, we can see that these limiting surfaces form a C2 alpha foliation of generalized apparent horizons. And so having constructed this solution, let me just briefly remark on some aspects of this solution. So we understand this jump behavior. So when our solution stays constant on a whole open neighborhood as via an outward optimization problem. And the main observation here is this proposition that the sub-level sets are always outward optimizing, but in fact, these sets U smaller or equal than T are always strictly outward optimizing, meaning our solution will exactly jump when the sub-level sets are no longer strictly outward optimizing. And then this new boundary, which we possibly create by jumping, is in fact a cylindrical C2 alpha generalized apparent horizon. So we can also use this flow to possibly detect such generalized apparent horizons. And the asymptotic behavior of these surfaces is as suspected that they are uniformly star-shaped in some sense as we move farther out, and in fact they become more and more round. And in fact, using further analysis, we expect to improve this result because these surfaces, these level sets should be close to these surfaces of constant spacetime mean curvature constructed by Cederbaum and Sarkovic, and they seem to they seem to have improved asymptotic behavior compared to other such foliations, and we expect that this should carry over to this kind of flow. And lastly, let me give a brief intro what we don't have. So uniqueness is still an open problem, and even for this elliptic regularization, because we have taken quite a few subsequences, and we hope to show that still all these subsequences, there's a unique limit, but this is what we're currently working. And also it would be interesting to remove this maximality condition to allow our function to be negative at some point, and then understand how and why this is negative and how this factors in. Yeah, thank you very much for your attention.
Great, many thanks for your talk. Is there any questions or comments for our speaker?
I have a question related to this generalized inverse mean curvature flow.
Yep.
In the usual approach, let me say the old one, since Gerhard, behind this gauge condition on this slice, there is some positivity of energy theorem. So there is some quasi-local mass or some integral over this two-dimensional leaf of this foliation, and there is some monotonicity of this quantity. If you assume that this slice is maximal, then perhaps here you have also some kind of positivity in this general gauge condition.
Of course we investigated. We try to investigate this, but so far of course the intuitive quantity would be just the Hawking energy. So replace the Hawking mass with the Hawking energy. But so far this seems to be not the case, neither for this inverse null mean curvature flow considered by Christian Moore, which is respect to this expansion, nor for our flow.
But in this smooth region also there is no monotonicity in the smooth part.
Yeah,
between two spheres, let's say.
No, even for the smooth case, monotonicity is unclear currently.
Okay. Mm-hmm.
One further quick comment or question?
Yeah, I have a question. So the point was to prove the Penrose inequality, right? So have you proved the Penrose inequality now, or?
I think this is related to the question just now. So of course, we would need kind of use some monotone quantity to fit this, but currently there seems to be no monotone quantity which we have studied right now to suggest such a Penrose inequality proof via this flow.
Right.
And how much? So of course, part of to get the Penrose inequality, one needs to get some control on the asymptotics, right? In any case, so that things are converged to things which are.
Yes, exactly. This core strategy of this proof by Huisken Ilmanen is this that the Gauge monotonicity of the Hawking mass survives this weak notion of inverse mean curvature flow. But still, even for the smooth case of either this flow by Christian Moore or ourselves, there doesn't seem to be a obvious monotone quantity.
Thank you.
Okay. I think we will go to the next speaker. Many thanks, Markus, for your talk.